Okay, so next we want to look at the application of the triple integral. Actually the same as we have done that on the previous video, but then we want to more specific on the cylindrical coordinate, which is finding the volume. Okay, actually as I mentioned before, so we can use the volume to using the triple integral, whether it is in Cartesian coordinate or cylindrical coordinate. Okay, so now in this question, okay, look at the 1A. Example on the finding volume using cylindrical coordinate. So the question A, you have to use the cylindrical coordinate to find the volume of the solid bounded by the given surfaces. So you have the surfaces of x squared plus y squared and also surface of z equal to 9. So z equal to 9 is a flat plane, and what is z equal to x squared plus y squared? So I don't want to repeat the procedure as we done in chapter 1. So this one is actually a bowl concave up, and actually the bowl is a very large bowl, but since we put z equal to 9, so at z equal to 9, so we have this plane. So this is z, this is x, and this is y. So the value here is 9 when z is equal to 9. Okay, so we want to evaluate the volume of this solid, where you can see that in this graph that I provide you earlier. This one, it looks like this. Okay, so now okay, I think I already skipped this one, right? Okay, but it's okay. I will go back to that. So just look at the volume here. So I will get back to this example after this. Just finish off the volume using cylindrical coordinate. Okay, so what is the formula? Finding the volume using triple integral. So 1 dV. Okay, so now you have to decide what kind of solid that we have here. So since here it looks like, okay, every time you want to deal with triple integral, please always put these small people just to guide you to get a correct order of integration, and also that you get correct region. Okay, so if you have this bowl with the cover, and then let's say as a normal people, you will standing like this, right? Okay, you will standing like that, meaning that the plane that you have now, right, on the floor that you have is lying on, or your lower bound is on the xy plane. So we can see that this is xy solid, which means that your dv should be dz dA xy. Okay, so now we look at the region first, about this one. So now talking about the region, so what is the region? The region is the dominant curve that you can see on the xy plane. What is the dominant curve that you can see on the xy plane? That's why last time I told you that, yeah, you said that you are standing inside the solid just to determine what is your lower bound and what is your upper bound. But in order for you to determine the correct region, you have to assume, let's say what is the dominant curve that you can see when you are standing outside the solid along the z, because you know that your region should be something that you can see on the xy plane. So that's why you have to take yourself outside and along the z, and you're looking down. What is the dominant shape? You can you just see this point, just the origin down here, or what is actually the dominant shape? Yes, you can see this circle when z is equal to 9. So that is your region. Okay, so I repeat, what is the region? The region is the dominant curve that you can see when you put yourself outside the solid. So you can see the circle centered at the origin when z is equal to 9. So, but then we have no idea at the moment what is the size of that circle. So you have to substitute z equal to 9 into the bold equation. So when z is equal to 9, what we have here is a circle with radius 3 on the y-axis plane. So this one is 3 and this one is 3. Okay, so that is your region. Okay, so they don't mention about the square root. I mean, they don't mention about the first octant. So meaning that you have to consider all. Okay, the complete circle. So now, based on your region, you can, which is your dA. Now we are talking about the region, which is dA xy, can be transformed into polar, which is cylindrical, because we solve in 3D. Sorry, in triple integral. So we have r dr d theta. So what is the limit of r? So 0 to 3. And what is the limit of theta? We have a complete circle, 0 to 2 pi. So now we have already the, okay, so dz r dr d theta, which means that now you have r dz dr d theta. So theta 0 to 2 pi, r 0 to 3. How about z? Okay, now for z, you have to look at your solid. Okay, look at you yourself inside the solid. So who becomes your lower bound? So now your lower bound is not flat. Last time we have so many examples that every time the lower bound is all the floor, right? The floor z equal to 0. But now this is not z equal to 0. This is part of the bowl. So what we can say that your lower bound is part of the bowl, which is x squared plus y squared. And your upper bound is z equal to 9. So, but then because we want to solve in cylindrical or polar, so you have to convert the limit of z into r and theta. So x squared plus y squared is r squared and 9 is 9. So then we can substitute the limit of z, r squared to 9. Okay, so now we have a complete triple integral in cylindrical coordinate. So now it's time for us to evaluate. Okay, so I'm going to explain in details all the steps, so I'm sure that you have no problem here, and you have to show that the answer will be 81 over 2 pi. Okay, so that is the volume for the first question. Okay. Next, we want to look at what is the solid. You have to know, so this is something not easy to be imagined, because now you see, okay, this one, okay, we have a bowl and we have the floor, but then you have, what is this? So this one is a cylinder, right? Cylinder, but the cylinder is not it's not the circle centered at the origin, but it's shifted somewhere. So we have to sketch so that we have a more clear vision. Okay, so we sketch. So we have the bowl, concave up. And actually the bowl is very, very large, but we just put in in this scale, for this scale. And then we have z equal to 0. So z equal to 0 is the floor. Okay, so that is your z equal to 0. And you have, okay, what is this? What is this? So it is basically, okay, we sketch the trace first. So y1 with radius 1. So we have a circle, this one is y, and this is x. So this is 2, this is 1, negative 1. And center of that circle is 0, 1. So that is your circle. But when you plot sketch on 3D, because after that we have to combine this all the surfaces together, so you have to make sure your orientation is the same, so that easy for you to imagine. This one is Z. So your circle, this is your circle. Cylinder. Okay, we have a cylinder. So now this is 2 and this is 1. Okay, so when you join this bowl concave up and this cylinder, then what you can have is, I will sketch the bowl. So you have a bowl. Okay, so that is part of the bowl. Okay, so this one may be part of the bowl concave up. So this one. Okay, so meaning that when you cut the cylinder by the bowl, so your sketching then become, so this is the cylinder and so that is part of the bowl. So this one is part of the bowl. Z equal to x squared plus y squared. Okay, so where is your Z0 plane? So Z0 plane will bound this. Actually your cylinder is very long, but then it's limited by the Z equal to 0, becomes the floor. So now this is closed actually. So this is actually closed. That is the solid. Okay, so we have to compute the solid, the volume of this solid. So this one is Z equal to 0. Okay, so now to get the volume using triple integral, you have to find the appropriate order of integration so that your limit will follow through. Okay, so now ask yourself, if you have this kind of orientation, so what is the orientation of you, where you will stand inside the solid, right? So what is your orientation? So I will standing in that orientation where my region should be lying on the xy plane. So in this case I have xy solid. So if you have xy solid, then your dv is dz dA on the xy plane. Okay, now we're talking about the dA area. Sorry, dA means the region. You want to focus on the region. So ask yourself, what is the dominant shape of the curve on xy plane that you can see when you take yourself outside the solid and you're looking down? What can you see? Can you see this shape? This shape, I don't know what kind of shape this one. Yes, you can see only the circle, right? Which is this one. When you're standing along the Z and looking down, the dominant region that you can see is this one. So meaning that from the trace here, this will become your region. Okay, so now based on this, so this become your region. So your region is lying on the first and second quadrant. Okay, so this is a part of circle, right? But the circle is not centered at the origin. It shifted somewhere. So meaning that in terms of limit of r, remember in polar for double integral, if you have a circle shifted somewhere, so your polar function, your r or your theta, normally r, so r is a function, not a constant. Okay, so if you remember the formula of Ross-Petal, symmetrical about the y, so in polar this is as the 2 sine theta. This is what I mentioned before. It is very important for you to memorize the polar function, the polar graph that you have learned in engineering maths 1. It is very useful. But if you don't remember, still possible to be done, but your task is becomes longer. You have to convert this equation into polar, into r and theta, which means that you have to expand the equation. You have x squared plus y squared plus 1 minus 2 y equal to 1. So you have x squared plus y squared minus 2y equal to 0. Then convert into polar. This one r squared minus 2 r sine theta 0, and we can factorize the r 2 sine theta. And we got two expressions, r0 and r equal to 2 sine theta. So we know that the graph should be this one. So r0 is just a dot. So the possible equation for this in polar is 2 sine theta. Or you can have this straight away if you remember the polar function based on the graph given. Okay. So now in terms of dA xy, we have to have r dr d theta, because the region is part of the circle or polar function. So now we have to solve in cylindrical coordinate. Okay, so what is the limit of theta and what is the limit of r? Okay, so the limit of r, how can we determine the limit of r? You draw a line starting at the origin. So your lower bound of r is 0, and the highest is coming from this curve. What is the equation of that curve? It is given by 2 sine theta. Okay. And how about theta? Theta is the angle. As you can see here, your region is lying, because it is passing through the origin, so it should be starting at x equal to 0 and then complete on the origin again, but only passing through the first and the second quadrant. So you have so in terms of theta, so theta 0 to 2 pi. Okay, first and second quadrant. So your limit of theta is 0 to 2 pi. Okay, so then we plug in so we have dz r dr d theta 0 to this is not 2 pi but pi. Okay, 180. Sorry about that. Just pi. Okay, so 0 to pi and r0 to 2 sine theta. Okay, now obtain the limit of z. You have to look at your solid here. Okay, so your lower bound is z equal to 0. And who is covering you? The covering you is this surface. So this surface is coming from the ball, which is x squared plus y squared. But you have to change in polar or cylindrical, so this r squared. So 0 to r squared. Okay, so now we can evaluate. So firstly, with respect to z, so r, z 0 to r squared drd theta r cube drd theta 1/4 r4 0 to 2 sine theta d theta. For sine theta 4 d theta. Okay, so you have to find a way to integrate the sine 4. Okay, so when you integrate the sine 4, you have to know the step. So sine 4 is same as sine square, right? Or sine squared, yeah, sine squared multiplied by sine squared or sine squared square. And then using the identity of trigo for sine squared. So this is the most appropriate identity can be used here. Because we don't want to deal with the square, right? So we want to reduce the power. So this is the most appropriate one. And then this one we square that, and this 2 square and 4 cancel out, and we have to expand this square. So we now we still have the square function here, but then we have to apply another identity of trigo for cos square. So this is another identity of trigo for cos square. Remember, this one is 2 theta, and this become double. So then and then you have to just you have to substitute this one and then simplify. You will get the you will get the 3/2 and so on here. So I'm sure that you can see this one, right? And then when you simplify, we have to integrate. So now they are all clear, right? No square anymore, just power 1. So we can start to integrate. So this one become 3/2 theta. Integrate cos, you will be sine 4 theta, cos also sine 2 theta over 2. Okay, where you can get from here. Okay, and then we replace the theta 0 to pi, and here this one is pi. This is for pi, sine pi. We know that sine 4 pi and sine 2 pi is 0. And when you substitute the theta equal to 0, so sine 0 is 0, sine 0 is 0, and this one of course 0. So that's why I just put the minus 0 here, and then this one becomes 0, and the answer is 3 pi over 2. So that is the volume for this particular example where the solid is this one. Okay, for C, we have to evaluate the surfaces bounded by the ball concave arc. It's very large ball actually, and cylinder radius 2. So this one is Z. And Z equal to 0 is the floor. Okay, so when we combine, so you have combined the ball and the cylinder. So because of the size of the solid depends on the size of the cylinder here, which is 2, and they will join together on the same at the same Z. Okay. So then if we read again, so the volume is bounded by the surfaces of the ball and the cylinder, and Z equal to 0. So where is actually your solid? So your solid is actually inside here. 1 and that 1. Okay. So if I resketch, so basically part the circle with radius 2, and you have the cylinder, and then that's part of the pole. right? So that is your solid that you have to evaluate the volume. So imagine you are standing inside this, or you have flying inside this. Okay, so now your region is lying on XY plane. So your dV is dz dE xy. Okay, so now about the region. What is the shape of the region? So the shape of the region is part of the circle with radius 2, centered at the origin, 2 on y-axis plane. So you can directly get the r 0 to 2, theta 0 to 2 pi. How about the z? The limit of z? So because the lower bound here is mentioned here, the lower bound is z equal to 0, which is the floor. So that is the floor. Your lower bound is z equal to 0, and your upper bound is you are covered by this plane, and also this plane, and this one is part of the bowl. Okay, the surface here is part of the bowl, so you have to put the bowl equation. So you have x squared plus y squared, and since our region is a circle or part of polar equation, so we can solve using cylindrical coordinate, where here is become r squared. So then we can determine the volume is r dz dr d theta, theta 0 to 2 pi, r 0 to 2, and z 0 to r square. Okay, so I'm not going to solve this, so please solve yourself, do it yourself, and I will give you the final answer for this. So that you will get is 8 pi unit cube, because now we are finding the volume. Okay, but if let's say you forgotten to put the unit, is okay, but if you put that, it's better. But I don't penalize you if you forgotten to put the unit. Okay, so in general, for the cylindrical coordinate, when we should use the cylindrical coordinate, normally if your region lying on xy plane and the shape of your region is part of a circle or polar equation, so the cylindrical and also the polar is the most convenient one to be used. Okay, so the next I back to the example here. So this one is the exercise on evaluate the integral by changing. Okay, now this one is the exercise to convert from Cartesian to cylindrical coordinate, and after that we have to solve.